Algebra 2, Section 1-4, solving inequalities. As I said in the last video about equations, where there was a chapter in Algebra 1, and we kind of cover that in one section in Algebra 2, it's much the same here with inequalities. There's a chapter that covers inequalities in the Algebra 1 book, and we're just going to try to catch you up to speed in one lesson here, so you're where you were when you left Algebra 1. And basically, solving inequalities is exactly the same as solving equations, with one major exception, or with one rule that you have to remember above and beyond that. And that rule is simply this: that if you ever multiply or divide both sides of the inequality by a negative number, you have to switch the inequality sign from less than to greater than, or greater than to less than or equal to greater than or equal to, or vice versa. And that's a rule that when you're actually doing the operations, it should be something that just kind of rings a bell in your head when you say, oh, I have to divide both sides by negative, ding, something goes off in your head, and you got to remember to switch the sense of the inequality. Here's a simple reason why. Is this a true statement? 6 is greater than 2? That's true, right? Now, if you pick any number you want and either multiply or divide both sides by that number, it's got to be negative. Pick any negative number that you want and multiply or divide both sides by that number, and watch what happens. I'm just going to pick the simple number -2, but you could pick anything. -2 times 6 is -12. +2 times -2 here is -4. Which one is greater? -4 is greater. The sense of the inequality has switched from greater than to less than. And that's just one anecdotal example, but that will happen in all cases, and we have to remember that as we're solving. It's going to happen in this first example here. First, we need to distribute. This would be 3x minus 15. Then we will subtract 3x from both sides. Now, not everybody would do that, and if you got a different method and you want to add 2x to both sides and make the left side 0, you can do that. It's going to be more work, but it does also avoid then the changing of the sign. Now, I don't think you should try to avoid it necessarily. You should just get comfortable with the rule. So I'm going to do this. Subtract 3x from both sides. You got -5x is less than -15. Notice we're keeping the less than symbol as we go. But now you're at the step where you're going to divide both sides by -5. And again, ding, did the bell go off in your head when I said divide both sides by -5? That's the place we want you to be. -15 divided by -5 is 3. Less than becomes greater than. And this is the solution. Okay. Now, I also said graph the solution. Graph until further notice means on a number line. Okay. So I like it very much when you include 0 on the number line and then one other number to indicate what your scale is. So I'm going by ones here. If I put a 5 at the fifth one, this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If you want to put another number there, you can. It's probably not necessary nor preferable to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Label every one. Okay, that can get really crowded. And greater than, if you list them as variable, inequality symbol, number, if the variable's on the left, you can think of this as like an arrow, and it's pointing in the way you're going to shade. So here's 1, 2, 3. Here's 3. Put an open circle at 3 and shading to the right. Okay. Now, I've seen teachers do this differently, and maybe you learned inequalities differently. If you like to put the circle on the number line and shade this way, that's fine. Make it clear though, right? If I did this and I just put it on the line and then I kind of just traced, and it's kind of hard to see that it's even on there, that's a little bit difficult as a grader. So you want to make it obvious, and also shade in the arrow so you're indicating that you know that it continues in that direction. I've also seen teachers and students do something like this, like that. That's totally fine. I've seen them do it like this, kind of coming off there like that. Whatever. I kind of prefer the first way. I did it best, but as long as I know what you're doing, that's going to be fine too. Okay. So that's graphing on a number line. And I do want to say something about a check, right? Because if you look at this number line, now this is kind of like a ray in geometry, and the end point is at 3, and the direction is to the right. So to check an inequality, and I'm not big on checking inequalities like, on the test or anything. I'm not going to ask you to check an inequality, but I want you to know that if you do check an inequality, you should check the number 3 as the endpoint and then the direction of the inequality. So here's what's got to happen. Negative 2x times 3 has got to be equal to 3 times 3 minus 5. Okay, so what I've done is I've taken the endpoint 3 and I've plugged it in for x. These should be equal because it's the endpoint. It's the 3. And what do we have? And I like what they did in the last lesson, put a little question mark there. We're wondering if they're equal. Here you have negative 6. This is 2 minus 5. That's negative 2 times 3 would be negative 6. So that part of it does check, right? So that's part 1 of the check. The other part is to check and make sure that we went the right direction, right? That this inequality symbol is correct, in other words. So we want to pick a number that's actually in this set, a number that's greater than 3. How about 4 or 10 or 100? It doesn't matter. I'll just pick 4. And is it true that negative 2 times 4 is less than 3 times 4 minus 5? And I'll even use the question mark here too. And this is negative 8. This is a less than symbol. And wondering if it's less than 4 minus 5 would be negative 1 times 3 would be negative 3. Is negative 8 less than negative 3? Yes, it is. That part of it checks as well. And now I know that this is the answer. Okay. Next example. I'll try to go a little faster. I'll distribute greater than or equal to 14 plus 7x. You go ahead and subtract 7x from both sides, and you've got 0 is greater than or equal to 14. Now, what do you think? What do you think's up with that? 0 is greater than or equal to 14 is a false statement, right? 0 is not greater than 14. Okay. In that case, what we're going to say is no solution. And interestingly, they asked us to graph the solution, and there is no solution. So what that would look like is simply a blank number line. Okay. And this is not beyond us to put something like this on a quiz or a test. So you would say no solution, and we could still make the number line worth a point, and you would want to leave it blank, right? If you graphed something, that wouldn't be correct. If there is no solution, we can't put any solution on the number line. Now, let me cover one other scenario. Let's say a similar thing happens, but you get 10 is greater than 5. On this line, 0 is greater than or equal to 14, which is false, no solution. What if you did the same thing and you got 10 is greater than 5 or 2 is greater than 1? Those are true, in which case the answer is going to be all real numbers. Everything would be a solution. It doesn't matter what x is, 10 is always greater than 5. So we'd say all real numbers. And what would the number line look on that? It would be everything. You would just draw a line with arrows. All real numbers is the entire number line shaded in with arrows going in both directions. Okay, moving on. We're skipping that example. This says graph the solution of 2x minus 1 is less than or equal to 3x, and keyword and, we're going to emphasize that more in the very next lesson that we do, and x is greater than 4x minus 9. So we're just going to tackle these one at a time. Go ahead and subtract 2x from both sides. That's probably what most people would do. Negative 1 is less than or equal to x. And I do like the variable to be on the left. This is the other reason you would ever switch the sense of the inequality, is if you just flip things around. So I like this to be x is greater than or equal to negative 1. I like the variable on the left for the reason that I stated earlier about it looking like an arrow. It's pointing to the right now. This is pointing to the right. Here, we would subtract 3x from both sides. Subtract 4x from both sides, and that makes this negative 3x is greater than negative 9. So divide both sides by a negative 3. Ding, x is less than 3. Now, you should carry the word and through your answer, especially through your work and especially in your answer, okay? Now, think about this on the number line. They said graph the solution of, and there's a key reason why. What numbers are both greater than negative 1, greater than or equal to negative 1, and also less than 3? There's only a certain segment of numbers on the number line that fall into this category. It's not all of them. You see, if I go to a number line, and here's 0, and here's negative 1, 1, 2, 3, here's 3, and I graph at negative 1, and it's going to be a solid circle. Oh, I think I didn't mention that on the last example that we graphed. Open circle is for less than and greater than. Solid circle is for or equal to's, less than or equal to and greater than or equal to. Here you have x is greater than or equal to, so you fill in the circle like that to say, yes, include this. If it's open, that means don't include this. That's for less than or greater than. So yeah, x is greater than or equal to -1. Here's -1. I've got a closed circle here, and I'm going to start shading this way. This one is x is less than 3, so you're going to start shading this way, and really it's just the interval in between. Only these numbers, inclusive of -1 and not including 3, but all the numbers in between, do fit into this answer. And this is key again to the word and it's going to be even more important in lesson 1.5. Only, so for example, 0, is 0 greater than or equal to -1 and less than 3? Yes, it is. What about 1? Yes. What about 2? Yes. What about 2.5? What about 2.9? What about 2.999? All of those numbers do meet this criteria. What about 3.5? What about 4? What about 6? All of those don't meet the criteria because they are not both greater than -1 and also less than 3. I'm trying to emphasize the word and when I say that. If it's greater than 3, it's not less than 3. If it was less than -1, you know, pick something like -2 or -10 or -1,000,000. It doesn't meet this criteria, and therefore they're not on our number line for a solution. Okay, so then there's one more thing that relates to that, and it's the word or. Okay, so we got a similar problem, but rather than and, it's or. The solution is it's either this or this, not and, not both, but one or the other. So let me just quick go to the answer here because you don't need to see me do the work again. Notice the word or is in their answer. That's going to be key. Okay, so this is the answer, and then the number line looks like this. And this is typically the way it happens. The and situation, they're coming together on a segment. And on the or situation, they're going apart. There are always exceptions to this, but by and large, this is what happens. And x is less than -4, open circle going to the left like they're showing, or x is greater than -2, open circle going to the right. Let me ask a similar question that I did in the last one. Can you think of any number that is both less than -4 and also greater than -2? That number doesn't exist, right? Because if a number is already less than -4, it can't also be greater than -2. If it's less than -4, it's to the left of -4 on the number line. It can't be greater than -2. And therefore, you're not going to have the segment coming together. You've got them going apart. A number is either less than -4 this way or greater than -2 going the other way. Okay? All right, thanks for tuning in. Until next time.